Stand up, Fanny. Stand up, Fanny. Stand up, Fanny. Stand up, Fanny. Stand up, Fanny.
Stand up, Fanny.
Stand up, Fanny. Stand up, Fanny.
Summer.
Stand up, Fanny. 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 Stand up, Fanny.
Stand up, Fanny.
Okay guys, let's come straight to the point. Why voltage remains constant in parallel circuit? In the previous video we have discussed why current remains the same in a series circuit. If you haven't watched that video, then the video link will be in the description. Make sure to check it out so that you will get much more deeper understanding of the topics I'm going to discuss in this video. So yeah, let's draw a simple parallel circuit which contains a battery and three resistors. Let's say the battery is of 4 volts and the resistor is of 1 ohm and the other is of 2 ohm and the other is of 3 ohm, and let's say the electrons flow in this direction. The conventional current flows in this direction. The conventional flow and the electron flow are in opposite directions. You must have known about this thing. Our scientists in the history, they have assumed that the current flows like this, but later they realized that the electrons flow in this direction, but they haven't changed the conventional current direction. So that's the reason, due to the history, that conventional flow of current has other direction and electron flow has other direction. So we are not talking about this conventional flow of current direction. We are talking about this electron flow direction. Some electrons will start flowing in this direction, and right here some electrons will flow into this 1 ohm resistor, and some electrons will flow into 2 ohm resistor, and some electron will flow into 3 ohm resistor. So what happens is this 1 ohm resistor resists a little bit resists these electrons a little bit, and this 2 ohm resistor resists more, and this 3 ohm resistor resists even more. So the resistance at this 3 ohm resistor is more. That's why less current flows here. And the 2 ohm in 2 ohm resistor, the resistance is much less than 3 ohm resistor, so there will be a little bit more current. And the 1 ohm resistance is much less than the 2 ohm and 3 ohm resistor, and that's the why there will be a little bit more current flowing towards here. So the currents in these three will be different. But why the voltage is different? Now before understanding why the voltage is different, first of all let's understand what is voltage. Voltage is basically potential difference. Now what is potential difference? Potential difference is literally the difference between potentials, the difference between potentials of two terminals. Let's say this is a terminal and this is the terminal, and the difference between potentials of these two terminals is potential difference, and that potential difference is voltage. Now what is potential? Now we have some potential here, we have some potential here. What is that potential? The potential is literally the work done by this battery in order to push electrons from this point to this point. So the work done to push this electron from this point to this point is potential, and we have some potential here and we have some potential here, and the difference between that potential is potential difference, and that potential difference is voltage. So now the concept of voltage is clear, right? So the work done, now the potential difference is voltage, which means the work done by this battery in order to move this electron from this point to this point is potential difference. That is voltage basically. So what happens is we have some current here. We have assumed that this battery is 4 volts, and this is 1 ohm resistor, this is 2 ohm resistor, this is 3 ohm resistor. Now there will be more current flowing through this 1 ohm resistor, and there will be less current flowing through this 2 ohm resistor, and there will be even less current flowing through this 3 ohm resistor, right? There will be different currents flowing through these three resistors. Okay, my English is not that perfect, guys, so okay, whatever. So there will be different currents flowing, and what happens due to the different currents is that there will be different amount of electrons flowing through this resistor, and there will be different amount of electrons flowing through this resistor, and there will be different amount of electrons flowing through this resistor. Now what happens is when there are different amount of electrons, there will be different amount of voltages. Now why this happens? Voltage is decreasing the work, right? Potential difference is like, what is the difference between the works done, right? A resistance resists the current, so basically right here it's 1 ohm, right? So it should resist less, and right here at 2 ohms it should resist more, and right at 3 ohms it should resist even more. So when resistance increases, the voltage should also decrease, right? Because they are resisting more. So more work will be done to resist them. So there should be some less there should be even less potential differences. So then why the potential difference is same? That's because the electron flow, the amount of electrons flowing here are more, and the amount of electrons flowing here are less, and the amount of electrons flowing here are even less. So it doesn't matter how much more this resistor resists, but the amount of electron flowing here is less. So even if the resistance is more, since the electron flow is less, and here even if the resistance is less, but the electron flow is more, that's why all these three balance each other. That's why we got the formula V is equal to IR, right? V, what is V? It's I multiplied by R. So V, literally this potential difference or voltage depends on both current and also resistance. So right here we have less resistance but more current, less resistance but more current. Right here we have more resistance but less current. So they in turn both balance each other, and the voltage right here and the voltage right here and the voltage right here, the voltage at these three places become the same. I hope you guys got.
Sorry, one more thing. It'll take 5 minutes. You don't have to remember it, but that's not what we were talking about yesterday. Remember, why voltages in parallel were the same. So if that's one resistor, and this is the other resistor, I'll take them here. And if this is 10, R equals 10, and this is R equals 5, and up here I've got a voltage of 10 volts. And that's my symbol for voltage. And that's my 10 volts. Which one of these is going to require the greater work of bringing charge across? Right, it's taking a minute or two to explain. Lower resistance, so if I'm bringing 1 coulomb across this guy, it's going to take less work or more work than bringing 1 coulomb across this guy. The first one will be less. So if I'm bringing the same amount of charge across both, well then you wouldn't say that the work done is the same in both cases, because there'll be less work done here than there is here. However, we know that if I collect I1 and that I2 and close the door. Yeah, so it's that little concept right there that we've just got to tease out, right? It's the work done in bringing charge from one place to another. Now, what do we mean by charge? Per unit, remember what is current? So current is a flow of charge. What's the basic unit of charge?
Coulomb.
The coulomb. And the current, what's the relationship between current? Because remember, it's I that's flowing here. What's the relationship between current and charge? Q equals, you got to have an I in there somewhere. Remember to quit? Q equals IT. So I equals Q divided by T. And it's this little bit here that we're going to try and make sense of up here. So the current is the charge divided by time. Now, if I'm looking at my current up here, if I'm saying the current here, I1, and the current here, I2, if this turns out to be, and we can work this out, if this turned out to be 2 amps, and I'll do the brackets to see because I haven't worked it out, what will the current up here be?
4.
Will everybody else take a look at that? If the current down here is 2 amps, and I should work this out mathematically, so I'm only guessing this. If that turned out to be 2 amps, what will my current up here be? Casper, what is it? It's less resistance, therefore it's going to be 4 amps. If it was 2 amps here, it would be 4 amps up here. Right? So whatever, the current there is going to be twice the current here. What do I mean by current? I mean the charge per unit time. So basically, there's going to be, in this case, twice as much charge per unit time past this resistor than there is past this resistor. So, and that's why the resistance is lower. You wouldn't hear? The resistance is lower, the current is doubled, and that means in per second, I'm going to be bringing twice as much charge. And that's what it means when I say by I. I is the charge, it's not the charge I'm bringing, it's the charge per unit time. And it's that little second there that makes a difference. That's why I explain it. So it's not that I'm bringing the same amount of charge to both resistors. It's that in 1 second, I'm bringing twice as much charge, twice as many coulombs per second here as I am here. And that's why the two effects are cancelling each other out. That's why you've got V equals IR. It's easy to say the current is twice it is down here, but what does it mean by current? It means the charge per unit time. And that's why we say the potential across there, the work done in bringing charge per unit time there is the same as the work done in bringing charge per unit time down here. Okay? Because there's less charge per unit time here, but there's more work done in bringing it across. There's more charge per unit time here, but there's less work done in bringing each coulomb. There's less work done in bringing each coulomb, which will bring twice as many coulombs per second up there as you are there. So it's not a definitive answer, but it just gives you another little extra bit.
Hey there guys, Paul here from theengineeringmindset.com. In this video, we're going to be looking at parallel circuits to understand how they work and how to calculate them. There's also some problems at the end of the video for you to try and solve. So we can connect components of a circuit in either series, parallel, or a combination of series and parallel. In these animations, we use electron flow, which is from negative to positive. But you might be used to seeing conventional flow, which is from positive to negative. Electron flow is what's actually occurring. Conventional flow was the original theory and it's still taught because it's probably easy to understand. Just be aware of the two and which one we're using. When we place a lamp in series or parallel with a battery, the electrons are going to flow from the negative terminal of the battery along the wire, through the lamp, and into the positive terminal of the battery. In the series configuration, there's only one path for electrons to flow along. If we place two lamps in a series circuit, they will both shine, but if one of the bulbs breaks, then the entire circuit stops working because there's only one path for electrons to flow along. You might have seen this with strings of lights such as ferrites. When one bulb pops, the whole string of light stops working. A solution to this is to wire the lamps in parallel. When we do this, we provide electrons multiple paths. If one lamp stops working, the circuit will continue to work except for the one broken path. Let's look at voltage first in parallel circuits. Say we take a 1.5 volt battery. If we use a multimeter to measure across the two ends, we will read 1.5 volts. But if we measure the same ends, we get a reading 0. Why? Because we can only measure the difference in voltage between two different points. Voltage is like pressure in a water pipe. If you fill up a tank and the water pressure is high, we can read the pressure of the pressure gauge. The gauge is comparing 2 points in order to know what the difference in pressure is. This will be the pressure inside the pipe compared to the pressure outside the pipe. When the tank is empty, there is no pressure difference because the pressure inside the pipe is not equal to the pressure outside the pipe. So therefore, we get a reading of 0. The same with voltage. We can only measure the difference in voltage between two different points. When we connect a component to a battery, it experiences the difference in voltage between the 2 points or terminals of the battery. The voltage or pressure will force electrons to flow through the component. In parallel circuits, the voltage is the same anywhere in the circuit. It doesn't matter if we connect a multimeter here, here, or here. We get the same reading. Why? Because each component of a path is connected directly to both the positive and negative terminals of the battery, so we receive the full pressure. pressure. In series circuits, the components were connected to each other, so the voltage reduced. But with parallel, there are multiple routes and each is connected directly to the battery. So when we use voltage in the formulas for parallel circuits, it's super easy because it's the same value. It's just the voltage of a connected battery. For example, in this circuit, the total current is 2 amps and the total resistance is 3 ohms. So what is the voltage of the battery? Well, from Ohm's law, we know that we need the formula voltage equals current multiplied by resistance. So voltage equals 2 amps multiplied by 3 ohms, which gives us 6 volts. Another example, this circuit is connected to a 12 volt battery. What is the voltage drop across the N lamp? Well, that's easy. We calculate voltage again by multiplying the current and resistance. It has a current of 1.5 amps going through it and a resistance of 8 ohms. 1.5 amps multiplied by 8 ohms gives us 12 volts. If we connect two 1.5 volt batteries in series, the voltage increases to 3 volts. Why? Because the electrons are being boosted by the second battery, so they increase in pressure or voltage. However, when we connect batteries in parallel, the voltage does increase. We only get 1.5 volts. Why? Because the batteries can't boost each other in this configuration. The path of the electrons is joined and it splits, so the flow of electrons are shared between the batteries. The batteries therefore can't provide more voltage. However, their storage capacity has increased, so they can provide 1.5 volts for longer than a single 1.5 battery by itself. We covered the basics of voltage in detail in our previous videos. Do check that out, links down below. So how does current flow in parallel circuits? Remember, current is the flow of electrons. We need electrons to flow in the same direction to power things like lamps. We apply voltage difference across the component to force electrons to move. As we apply more voltage, more electrons will flow. The speed of electrons remains the same, but the amount of electrons moving will vary. The more electrons we have moving, the higher the current. We represent current with a capital letter I, and we measure current in needle amperes, but we usually just show it to say amps. If we connect a lamp with a resistance of 1 ohm to a battery rated at 1.5 volts, the total current in the circuit will be 1.5 amps. We can measure that by placing a multimeter into the circuit, or we can calculate that using Ohm's law, and the formula current equals voltage divided by resistance. We won't go into too much detail on Ohm's law, we cover that in a separate dedicated video. Do check that out, link down below. If we then connect a second 1 ohm resistive lamp into the circuit while in parallel, the multimeter reading the total current sees an increase of 3 amps. But if we measure the current through the lamps individually, we see the multimeter will read just 1.5 amps on each. In the wire between the two lamps, we also see a current of 1.5 amps. We can see that the current will divide, and if we measure the current reading the total in a separate dedicated video, do check that out, link down below. If we then connect a second 1 ohm resistive lamp into the circuit, check out, we won't go into too much detail. We can measure that by placing a multimeter into the circuit, or we can calculate that using Ohm's law, and the formula current equals voltage divided by resistance. We won't go into too much detail on Ohm's law, we cover that in a separate dedicated video. Do check that out, link down below. If we then connect a second 1 ohm resistive lamp into the circuit while in parallel, the multimeter reading the total current sees an increase of 3 amps. Amps. But if we measure the current through the lamps individually, we see the multimeter will read just 1.5 amps on each. In the wire between the two lamps, we also see a current of 1.5 amps. We can see that the current will divide and the electrons will flow in all the different routes available to get back to the battery, and then they will recombine. We can also see that the total current is the sum of the current in each branch, so we calculate the total current using the following formula. If we replace lamp 1 with 2 ohm resistive lamp, that's now double the resistance on that branch. Then the total current decreases to 2.25 amps. Lamp 1 sees a current of 0.75 amps and will be less bright. Lamp 2 continues to read 1.5 amps, and the meter between lamp 1 and 2 continues to see 1.5 amps. Therefore, we can see that the current flowing in the branch depends on the resistance of the branch, and again, the total current in the circuit is the sum of the currents in each branch. If we add a third 1 ohm lamp into the circuit and we change lamp 1 back to a 1 ohm resistive lamp also, so that's now 3 1 ohm lamps in parallel, we see that the total current in the circuit is now 4.5 amps. Each lamp continues to see just 1.5 amps of current. The multimeter on the wire between lamps 1 and 2 has increased to 3 amps, but the meter between lamps 2 and 3 reads just 1.5 amps. If we double the voltage from 1.5 volts to 3 volts, then the current will double also. The total current increases to 9 amps, the current between lamps 1 and 2 increases to 6 amps, and each lamp now experiences 3 amps of current. So from this we can see that the voltage applied will vary the current. The total current also varies with the resistance of each branch and how many branches are connected. Let's see some more detailed explanations on how to calculate this. See if you can solve this before I do. Take this simple parallel circuit with 2 resistors and a 12 volt battery. Resistor 1 is 15 ohms and has a current of 0.8 amps. Resistor 2 is 24 ohms and has a current of 0.5 amps. So what will the multimeter read for the total current? In the circuit. Well, we know that the total current in the circuit is equal to the sum of the currents in all the branches. Therefore, 0.8 amps plus 0.5 amps is 1.2 amps. What if we know the total current and the current in one branch? How do we find the current in the other branch? Well, that's easy. We just subtract. So in this example, we have a 12 volt battery connected to 2 resistors. The total current is 3 amps, and branch 1 has a current of 1.8 amps. The current in branch 2 is therefore 3 amps, subtract 1.8, which gives us 1.2 amps. How do we calculate the current in a single branch? We use the formula current equals voltage divided by resistance. Let's say we have 3 resistors wired in parallel to a 6-volt battery. Resistor 1 is 10 ohms, resistor 2 is 2 ohms, and resistor 3 is 5 ohms. What's the current flowing through each? Well, let's look at resistor 1 first. Current equals voltage divided by resistance. So 6 volts divided by 10 ohms gives us 0.6 amps. Resistor 2 is 6 volts divided by 2 ohms, which is 3 amps. And resistor 3 is 6 volts divided by 5 ohms, which is 1.2 amps. So the current in this part will be 1.2 amps because there's only the current from the single resistor. The current in this wire will be 4.2 amps because there's the current of resistor 2 and 3 passing through it. The current here is the total current, which is 4.8 because of the current in all 3 branches flowing through it. Okay, so how do we calculate the total resistance in a parallel circuit? This is the part which people struggle with the most. It looks difficult because of this formula, but it's actually very easy and I'm going to show you how. And to make it even easier, we built a free online calculator for you, and this will help you find the total resistance in your parallel circuit. You can find links to this in the video description down below. In a series circuit, the total resistance of the circuit was the resistance of each component just added together. Why? Because the electrons had to pass through each one, so the more resistors they passed through, the more total resistance increased. But with parallel circuits, we're providing lots of different paths for electrons to flow through. So we're instead going to work out how conductive each branch is, or how easily electricity can pass through each branch. We then combine these values and we convert that back into a resistance. Let's take this simple parallel circuit with 2 10 ohm resistors. How do we find the total resistance of the circuit? Well, we have to use that formula, which is RT, or resistance total, equals 1 divided by 1 divided by R1 plus 1 divided by R2. So we then replace the R1 and the R2 values with our resistor 1 and our resistor 2 values. So we start at the bottom and we divide 1 by our 10 ohms for both, which gives us 0.1 plus 0.1. So we add the 2 decimals together to get 0.2. So then we just divide 1 by 0.2 to get 5 ohms of total resistance. If you do this in your calculator or in Excel, then just remember to use your brackets. So although we had 2 10 ohm resistors, the total resistance is only 5 ohms. That's because the current has been split and so the resistance has reduced. If we had 2 5 ohm resistors, then the total resistance is 2.5 ohms. If we had a 10 and a 5 ohm resistor, then the total resistance is 3.33 ohms. If we have more resistors, then we just keep adding them into the formula. We input our resistor values and we get again 3.33 ohms. For example, a 10 ohm, a 5 ohm, and a 2 ohm resistor gives us a 1.25 ohms total resistance. So why are we using all these 1 divided by resistor fractions in the formula? Well, you don't really need to remember why we do it, you just need to remember how to use the formula. But I'll just explain briefly why we do it this way. Because there are so many paths for the current to flow through, we instead work out how well electricity can pass through each path. That's the conductance, which is the opposite of the reciprocal of resistance. As we already know the resistance value of the resistors, we can just invert this value to find the opposite. Looking at a 10 ohm resistor, we can also write 10 equals 10 divided by 1, because 10 divided by 1 is 10. And you can do that with any number. Then we invert the number to find the conductance of the reciprocal, and we do that by flipping the denominator and the numerator. So we get 1 divided by 10, which is 0.1. We can flip it back to resistance by gain divided by 1, because it's the opposite. So 1 divided by 0.1 is 10. If we had a 1 ohm resistor, then we have a conductivity of 1. If we had a 1000 ohm resistor, then we have a conductivity of 0.001. So you can see that it's going to be easier for the electricity to pass through the 1 ohm resistor because it has a better conductivity. So once we work out how conductive each path is, we add them together to find our total conductivity. As we saw a moment ago, we can convert that back to resistance by taking the reciprocal. So 1 divided by the total conductance gives us our total resistance. Hopefully that made sense. If it didn't, then don't worry about it too much. You're never going to really need that. You just need to use the formula. Power consumption in parallel circuits. The resistors and the components will convert the electrical energy into thermal energy as the electrons pass through and collide within the components. That's why they become hot, and we can see that using a thermal imaging camera. So how much power are the individual components and the circuit in total consuming? We can use 2 formulas for this, either voltage squared divided by resistance or voltage multiplied by current. Let's see some examples. Say we have a 10 ohm and a 5 ohm resistor connected in parallel to a 6 volt battery. R1 has a current of 0.6 amps. That's 6 volts divided by 10 ohms, which gives us our 0.6 amps. So the power consumption of the component is 3.6 watts, and 6 volts squared equals 36, so 36 divided by 10 is 3.6 watts. Alternatively, 6 volts multiplied by 0.6 amps also gives us 3.6 watts. R2 is 5 ohms with a current of 1.2 amps. That's 6 volts divided by 5 ohms, which equals 1.2 amps. So the power consumption is 7.2 watts. We see that from 6 volts squared divided by 5 ohms. 6 volts squared is 36, so 36 divided by 5 is 7.2 watts. Alternatively, 6 volts multiplied by 1.2 amps also gives us 7.2 watts. The total power consumption is therefore 3.6 watts plus 7.2 watts, which is 10.8 watts. We could have also found this by multiplying the voltage by the total current, or alternatively, we could have used the voltage squared divided by the total resistance. Okay, now let's see if you can solve these problems. I'll leave a link in the video description for the answers and the solutions. Question 1. We have 4 resistors in parallel, a 10 ohm, a 20 ohm, a 2 ohm, and a 3 ohm. What is the total resistance of the circuit? Question 2. We have 3 resistors connected in in parallel to a 6-volt battery. The total current in the circuit is 2.5 amps. Resistor 1 is 10 ohms with a current of 0.6 amps. Resistor 2 is 15 ohms with an unknown current. And resistor 3 has an unknown resistance value and an unknown current. Calculate the current flowing in resistor 2 as well as the current.
Suppose you are given this messy electrical circuit with a battery here and a bunch of resistors connected in what looks like a confusing web of series and parallel connections. Then someone comes and says, hey, I want to measure the voltage and current at each resistor, like say if I connect a voltmeter, which measures the voltage across 2 points, at this 15 ohm resistor. I want to know the value of the voltage that it will show. Similarly, if I connect an ammeter, which measures the current across 2 points, beside this 8 ohm resistor, then what will be the value of current that it will show? Before we begin, let me give you a quick revision about voltage, resistors, and current, such that using only these basic concepts, you can confidently tackle even the most complex-looking circuit step by step. You will never need anything else. If we have a resistor and a current flows through it in this direction, then the resistor acts like a voltage eater. It munches on some of the energy from the battery, and this is called a voltage drop across the resistor. The voltage drops in the direction of the flow of the current. So, if the current goes left to right, the left side of the resistor is at a higher voltage, and the right